All right. Today we're going to finish our discussion of query optimization. And what I wanted to do, the slides are quite dense, so rather than review the slides, I thought we'd spend a little bit of time just on the board going over the basic concepts from last time to enable us to kind of finish up this time and move on. Query optimization, as I told you last time, is a technology that has three distinct components, each of which can be designed relatively independently of the others and understood relatively independently of the others, which is nice. So I want to take them one at a time. We'll, at a very high level, remind ourselves what we learned about each of these components of the optimizer. And then we'll go back and finish our discussion of, I believe we were talking about cost estimation, and then we'll do the search strategy. So to begin with, we have to have a plan space. This is the space of all legal plans for a given query. So you give me an SQL query, there is a space of possible plans that we would consider for that query. Now, in any language, relational or any other declarative language, there is such a space. And typically, we might look at the whole space, or we might choose heuristically to only look at parts of that space. And what we said last time, based on the System R optimizer, is what we're going to look at in the plan space is these left deep join trees. Okay? Where the right-hand side of every join is a table. Something like that is a left deep join tree. Okay, so the right-hand side of every join is a table. And we know from the algebra equivalence that joins are commutative and associative, which means that we can take joins and we can flip the children, they commute, and we can also perform the associativity transform on this. So this one is S join T, join R, which is the same as S join T join R, which looks like this, right? So the two transforms we can consider are this one, flipping these two guys, or converting this to that, which is actually not a left deep tree anymore. True? Okay, but from here, we can use commutativity to flip this one to be on the other side, and that's going to give us T join R join S. All I did was I took S, and I pulled it over to the right-hand side of this join, and pulled this subtree over to the left-hand side of this join. So you can actually go from here to here in 2 steps, T, R, S. And in general, if you play this game a lot, what you'll see is that through commutativity and associativity, the space of all the left deep trees that you can have is a choice of an outer relation, and then any order of the other relations as inners in a join pipeline. Right? So the space of left deep trees is this, and, well, keep S as the outer and reorder the joins. Right? So all I did was I took this thing and this thing, and I reordered them. Okay? So you can reorder all these things above S, or you can pick a different thing as the outermost, T, join R, join S, and you can then take all orderings over T, etc. So the space of all left deep trees that you can get through commutativity and associativity is a choice of an outermost relation and a permutation of the other relations. Understood? And that comes from our algebra rules that join is commutative and associative. Okay, so the space is all left deep trees. I'll leave one left deep tree on the board for you to look at. In addition to the shape of the plans we'll look at, we've got various access methods for the leaves. So B trees on various columns that may or may not be defined in your database. If you do have the B trees, great. As well as heap scans. And then we have various join algorithms, right? And then one final detail. Remember from our relational equivalences that you can push selections below joins and you can push projections down as well, as long as you preserve the columns you need later on in the query. So the way we'll talk about this, because those are possible, we'll have a heuristic in our optimizer, which is selections and projections as low as possible in these trees. And by low, I mean as close to the leaves of the tree as possible. Okay? So we'll always be projecting out columns that aren't needed higher up in the tree. We'll always be applying selections as soon as we have the attributes that we need to apply those selections. So this is the plan space that we're going to consider. And the reason we can enumerate this plan space is because we understand the relational equivalences, which allowed us to talk about commutativity and associativity of joins. They talk about the correctness of the selection and projection pushdowns. Okay? And then the physical implementations of those operators as well. So it's the logical choices. This is a logical optimization, pushing selection and projection before join. This is a logical optimization, the fact that you can commute and associate joins. And these are physical. The ones with pluses are physical transformations. They're physical choices of what algorithms to apply and what data structures to use. Okay? So that's our plan space for these relational queries. If you build an optimizer for a different kind of declarative language, you might have a different plan space. Right? And it'll be grounded by the things with the stars, your logical equivalences, and the things with the pluses, your implementations in your system. Note, suppose you have your database, you decide to add a new join algorithm to it. That's good. All you do is you have to tell the plan space there's a new join algorithm. You just kind of plug it in here. It's another option for join algorithms. Everything else is going to continue to work. You're going to need a cost model for that join algorithm as well. But otherwise, everything else is independent. Define a new type of index, same story. Just teach the system that it exists, teach the system its cost, and off you go. All right, so it's quite pluggable. And if you define a new part of your language, then you'll have to define maybe new shapes of trees or new transformations you can do to these algebras. So that's your plan space. The cost estimation piece of the, well, actually, before we go on, any questions here? Okay. The cost estimation piece of the puzzle is the costs of individual operators, which we've been studying all along this semester. So individual nodes in these plan trees, right? And we have to be able to estimate the output cardinalities, the number of rows in the output for these operators, right? Because the output of one operator is the input to the next, and the costs are defined in terms of cardinality, in terms of the number of rows. We also probably need to know the output size in bytes, right? So you need to know the number of rows and how many bytes they occupy. And those are the inputs to the next guy's cost. So we'll need a way to compute the output of one operator because it's the input to the next operator, right? So this is done through what's called selectivity estimation, or what the book calls reduction factor estimation. Okay? And that's going to be based on information we store in the catalogs about the stored relations and formulas that we have for computing output cardinalities based on input cardinalities. So the base case of this is the base relations in the database and the metadata we have about what's in them. And then the inductive case, where you're computing the input to something higher up in the tree, has to do with these output cardinality estimation. Okay? You can spend a lot of time making this piece of the system better. We'll talk about that in our first slide today. But it won't really change this at all. And it needn't change this stuff either. Okay? so that you can kind of work to make this smarter. And if you're unhappy with the class discussion because it was relatively naive here, that's fine. You just kind of make this stuff better. All the rest of the framework continues to work. Finally, the search strategy we'll look at today. There's actually multiple search strategies in the literature. Something I actually was really excited about when I was in grad school was different, more efficient search strategies. The one we're learning is the System R search strategy, or sometimes called the Selinger search strategy after Patricia Selinger. Oh, sorry, Selinger. I always said her name wrong. She pronounces it Selinger. And this is a dynamic programming algorithm. This is not the only algorithm used. Actually, there's one other one that's quite common, which is called cascades, which we won't learn in this class. But it's used in a bunch of products, and it's used in some open source as well. There's an interesting open source project, if you want to look at it, called Calcite, which is a cascade-style query optimizer and an execution engine that can run over many different environments. It's sort of a query engine for lots of different things. It could be Hadoop file system. It could be files on your desktop. But the key of that project is a cascade-style query optimizer. That's what Calcite is mostly. We're learning this one, which these two strategies are the most widely used. This was the name of the first system that implemented this scheme. We won't have time to talk about it. There are other things that are used, which are usually heuristics of one kind or another, and less exhaustive. These are both exponential time exhaustive algorithms. And then there's heuristics that are usually polynomial time. All right, there's a variety of them. Postgres implements System R and a heuristic. The heuristic it uses is a genetic algorithm, which probably is bad, to be honest, because genetic algorithms tend not to work very well. They're sort of unprincipled. But someone built it, and it got supported, and it's in the system. Postgres will use the System R algorithm for queries up to a certain size. That is to say, up to a certain number of tables, like 10 or 12. I can't remember what the limit is. If you have too many tables, it falls back to this heuristic optimizer, which does whatever it does. All right. Last I checked, MySQL and SQLite were simply heuristic optimizers. They didn't do any cost-based optimization like this. Generally speaking, the scheme we're describing is sometimes called cost-based query optimization because you actually try to estimate the costs of things. You don't just use heuristics. OK, so this kind of lays out the framework. We spent a bunch of time talking about this last time. And we spent a fair bit of time on selectivity estimation. OK? And where we're going to pick up in the slides now is to talk a little bit about how to make selectivity estimation somewhat better. And then we're going to move into the search strategy discussion of the System R optimizer. OK? And that'll round out our discussion of query optimization. Any questions on kind of the structure of this whole discussion or any of these components at the level we just discussed? Yeah? I'm sorry, repeat the question? The question was, of these three parts, which takes the most time? And actually, that's not an easy question to answer. So this doesn't have any computation in it. This is a parameter. This is an input to the problem, if you like. OK? This does, you call cost estimation along the way while you're doing the search strategy. So this becomes kind of a subroutine that you call here. And you'll see that when we talk about System R, it's going to prune the search along the way. How does it prune? By costing things, by saying, oh, this thing is cheaper than this thing, I'll throw away this thing. So it's going to call cost estimation along the way to decide what to prune. And so you can ask, during search, how much of the time spent during search is on cost estimation? So that's a better formed version of your question is all. This is usually pretty cheap. But it can get exponentially expensive if you start getting too statistically fancy. So if you try to model the statistics of your database to do really accurate cardinality estimation, you can very easily come up with models that have exponential cost. Most people don't do that as a result, and that's one of the reasons to be sloppy here, is to keep the cost estimation cheap. Okay. The search strategy, as we said, the problem of finding, even just for a query with just joins, finding the best join order is NP hard. So this is an exponential. Both of these are exponential algorithms. So they make exponentially many calls to this. among other things. They also look at exponentially many plans. And it's exponential, I should say, in the number of tables in the from clause, just to be real clear. Other questions? Okay. With that introduction, let's refine our selectivity estimation by looking at some somewhat more sophisticated metadata we can store in the catalogs. So if you remember our discussion last time, we stored very simple things in the catalogs. We stored this. Oh, you know, this. It's right here. Put it on the big screen. We stored things like the number of tuples in each table, the number of pages in each table, the minimum and maximum values in a column, the number of distinct values in a column, how tall each index is, how many pages there are in each index. Very simple statistics. Now, one thing we'd like to know for selectivity estimation is what's going to be the number of tuples in the output of a selection, let's say. Okay? So if I tell you with this data that we have a selection of the form, this is not going to work. That's not going to work. Select star from sailors where rating is greater than 5. We saw this last time. And we knew that ratings minimum is 1 and maximum is 10. And there are 10 distinct values in that range, 1 through 10. Okay. Then you might say rating greater than 5, 6, 7, 8, 9, 10, is 5 of those 10 values. Okay, so we know that. But how will we estimate how many sailors have that rating? Well, with this information, what do we know? We know that very little, really, is the truth. We know things go from 1 to 10. We know that they go by integers, right? 2, 3, 4, 5. And we know how many tuples there are. So this is the number of tuples. This area is the number of tuples in the table. And we're assuming they're evenly divided across each one of these values. It's like a bar chart in which each one of these bars is the same height, and each one of their widths is the same width, right? That is a uniformity assumption. We're assuming a uniform distribution of sailors to ratings, right? And with such a uniformity assumption, we'll assume that this much of the table is half of the sailors, because it's half of this bucket. Agreed? Everybody good? This is pretty naive. So an obvious thing to do better would be to store information so we don't have to make uniformity assumptions. There's lots of ways we could do that. One way we could do that is we could store a parameterized distribution, which is to say a mathematical function which has some parameters, and those parameters would describe the distribution. So the classical parameterized distribution would be either called a Gaussian or a normal distribution, or in common parlance, it's the bell curve. And it's described by a mean and a variance. It's a different sigma than selection, okay? And it's a distribution that looks like this, right? So we have sailors go from 1 to 10. We want to know what's the mean. Maybe it's there. Actually, probably it's down here. And the variance will tell us how wide the bell is, all right? And the mean is in the middle of the bell. And it's symmetric. And you've all seen this guy before, right? This is except that it's maybe truncated. Okay, so this is like a Gaussian distribution. We could have things like that. But then we have to fit curves to our stored data, right? So we have our stored data. We'd use that data to learn a mean and a variance. We could store the mean and the variance. This is an option. This is not actually what most database systems do. They don't use parameterized models. They use non-parametric models, which are things that are not math formulas with parameters like this. They're just descriptions of the actual stored data, all right? So a description of the actual stored data that's quite common is a histogram. Right, which just counts up in a bunch of buckets how many things fall into that bucket. And that's kind of what I was alluding to in this picture. Okay. So a decent histogram for this data might be, here's the number of sailors with rating 1. Here's the number of sailors with rating 2, rating 3, rating 4, rating 5, 6, 7, 8, 9, and 10. Right? And so you can store a histogram like that. And now when people ask how many people have a rating greater than 5, you look at these buckets. 2, 3, 4, 5, 6, 7, 8, 9, 10. And you count up, you add up their heights, right? And then you get an answer that way. So you can certainly store histograms. And then you get into the game of what's a good kind of histogram to store. It actually matters, okay? So there's the typical histograms we tend to think of are equi-width histograms. So the picture on the upper part of this example on screen, where every bucket has the same width, and we simply count up how many things fall into that bucket. So the bucket boundaries are defined in advance, and usually they're defined as a uniform partitioning of the domain. Things go from 1 to 10, we'll have 1, we'll have 2, we'll have 3, we'll have 4. Or if things go 1 to 1,000 and we only have 10 buckets, we'll do 1 to 10, or 1 to 100, sorry, 100 to 200, 200 to 300, et cetera. So we split up the domain into equal widths, and then we just count up with a group by query how many tuples fall into each bucket. Yeah? So that's equi-width histograms. And there's an example of one there. All right, you can see it's got values and a count, or a number of values, number of tuples with that value. Oh, no, sorry. Yes, number of tuples. It's probably where it says number of values on this slide in those rows. It should probably say number of tuples. The alternative, actually, is to have, an alternative, I should say, is to have equi-depth histograms, where the width is variable, but every bar is going to be the same height, or maybe one off of that height. You get off by one error, so you can't force it to all be exactly the same. It can be within one of the same. All right, so here's an equi-width histogram where each one of these buckets may cover a different range of values. So the first one is 1 wide, the second one is 1 wide. But as you get to the right, there's some buckets that are wider, 5 to 7, okay? Because there's not as many values over there on the right. So it takes a wider bucket to grow up that high, right? And so these equi-depth histograms are capture information differently. And there's trade-offs between these in terms of how well they perform on estimation problems. One thing to think about, which is the point at the bottom of the slide here, is that equi-depth histograms are kind of like order statistics. They're like medians and quantiles. Because what it means to have 10 buckets of equal depth is to say 1/10 of the data is in the first bucket. That is the first decile of the data. 2/10 of the data is in the second bucket. If you take the buckets that are halfway to the left, then where you are, that is the median of the data. All right? And if you know anything about like looking at grade scores and stuff, you'll know that medians are very robust to outliers. So equi-depth histograms perform nicely if you're trying to estimate things and you're worried that there's outliers in the data that are going to skew stuff crazy. Okay? To think about an equi-width histogram, if there's one crazy outlier value way over here on the wood, it's going to stretch this whole thing out, right? Because we want each one of these to be equally high. And you're going to have a whole bunch of teeny buckets over here. And then you're going to have a bunch of not very information-rich buckets that are very tall over here, right? So equi-width is more sensitive to outliers. Just some intuition here. But on the other hand, they do pretty well capturing things like normal distributions, which are quite common in practice. And they're easy to implement, okay, because all you do is that group by query. Whereas equi-depth histograms, you have to do a median query, which if you recall correctly, you have to do quantile queries. If you recall correctly, it's harder to implement. So there's trade-offs, and you can read research papers about which ones of these are better. And there's actually other kinds of histograms that have been defined. How do you define the bin boundaries? I'll leave it with that, though. You've seen at least an example. Now, when you want to compute the size of a join, if you remember correctly, the way we computed equality, remember the bunnies? The way we computed equality predicates, like column 1 equals column 2, that's a join predicate. So, or it could be a join predicate. So if you take this query and you modify it to include the ratings table, I'm sorry, the reserves table, sailors S, reserves R, this is S.rating greater than 5, and R.SID equals S.SID. The selectivity of this predicate, we said, was 1 over max of n keys, et cetera, et cetera. That's fine, but if we know something more about the data than just its extent, we can be more clever. So if we have two histograms that we're sort of joining, this is one data set, one table. This is the join. This is SID. This is R.SID. Let's say. So this was rating. Let's repurpose this picture. So this histogram that you see here is now sailor IDs. in the reserves table. Okay? This picture I'm about to draw, let's do it on this board. This is going to be s.sid. This is sailor IDs in the sailors table. This may not work, but we'll try. Very sloppy. These are all bars. These are not little mountains. All right. So this is s.sid. And now the join of these two things, we can line up the buckets from these two. This isn't going to work, darn it. But you can imagine if this goes from 0 to 1 million, and this goes from the same range, 1 million and 0, there's no reservations from anyone here in the sailors, okay? There's no reservations from anyone from here to here in the sailors. All the reservations from sailors are here, and there's some fraction of these buckets. Then we should be using the reasoning that's on this slide, but we should be using it with respect to the overlap of these two histograms, right? Only in this range, and then taking account for how many reservations there are relative to how many sailors there are, bucket by bucket, not over the entire table. So that 1 over max would be applied bucket by bucket and worked out that way. Does that make sense? So the histograms allow you to take what this thing is, which is really one. The uniformity assumption is a 1-bucket histogram. It assumes all the data is in one rectangular bucket. And to think about histograms for, that are more than 1 bucket, you just take them a bucket at a time. You say, for this bucket, which matches this one from r.sid, what is the overlap we'd expect? How many join tuples would we expect in the range from here to here, here to here? And then you do the same thing here, and the same thing here, and the same thing here, et cetera. Okay, so you just call this logic bucket by bucket and add them up. Question? Ha 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 ha. You anticipated my next point. If you have equi-width histograms and you're careful that every table bins things the same way, then this works great. If you have equi-depth histograms, by definition, the bucket boundaries aren't going to be the same. Because the whole point with equi-depth histograms is you move the bucket boundaries around to get all the buckets the same height. And then you got a problem, because the R buckets and the S buckets don't line up right. And now you have to estimate how you deal with overlapping buckets. And that algorithm I just described is kind of, now you have to do this estimation problem of how much of each bucket do you apply to which parts of the other table, la la la. It's complicated. I don't even want to think about it right now. So no, in general, you can't assume this. But if you design your histograms as equi-width and you're disciplined about keeping your widths the same across things that will join, then you can always go bucket by bucket. Okay, so it's another reason to use equi-width is it fits these kinds of computations nicely. Otherwise, you get estimation problems on unaligned bucket boundaries. Good. Okay. There's this rabbit hole goes very, very deep. Okay, you can work on this problem a lot, and there's a lot of really fun computer science and mathematics to go do this, which I won't talk about in this class. Except maybe to write one word on the board, which is an alternative to, two alternatives to histograms. It's one alternative for modeling your data in a non-parametric way. Another one is to do what are called sketches. And I don't have time to talk about them, but there's a really cool branch of sort of approximation algorithms that's roughly called sketches or synopsis data structures, synopses. That are really great. And if you're curious about estimation problems in querying generally, you want to know about sketches. The other thing people sometimes do is they sample the data. So rather than storing a histogram, or maybe you never computed one in the past, you randomly sample the data to try to get a sense of what the distribution looks like. So sometimes people will use samples of the actual data to try to predict what's going to happen for costs over the whole data. All right, and again, the rabbit hole goes really deep. You can work on this for a long, long time. All right, and I won't go through any of this. But you've at least seen histograms a little bit. I will not hold you responsible for being able to do estimations over histograms. When we do homework assignments, et cetera, we'll stick with this kind of Selinger 1979 one bucket estimation problem. Okay, and we'll just leave it there. But I do want you to know, as educated database experts, that your cost estimation, this middle board, could be a lot more sophisticated. Okay? Great. All right, which takes us then to the third board, search strategy. Nope. There we go. All right. So let's talk about search strategies. And as I said, we're going to use the System R or Sellinger search strategy. All right, there's really two cases. We're going to break the problem into two parts. There's going to be a base case and an induction case, because it's a dynamic programming algorithm. Dynamic programming is an inductive process. You start with the bottom of your dynamic programming table and you build it up, right? So how do you fill in the bottom is the first part, and how do you recurse and build it up is the second. So we'll first look at plans for single relations. So if you write a query with 6 tables in the where clause, the first thing we're going to do is imagine one table at a time what we'll do for the individual tables. Then we'll start putting them together in pairs, in triples, in quadruples, in quintuples, until we get the best plan for 6-way, and then we're done. Because the best plan for 6-way is the best plan for the whole query. All right, so we'll start first, though, with single tables. And when you think about single tables and you pretend that your 6-way join query is really just 6 one-way queries, the only things you can do on a single table are consider what access path you're going to use. So are you going to look at a B tree or a heap file? Which B tree? You know, how much does it cost to evaluate the predicates from the query on that B tree? Okay, and you want to choose the one with the least estimated cost. And we're going to do that just for the single table access. We're going to find the cheapest way to access each table individually. We will do selection and projection as early as we can in the Sellinger algorithm. So we're always, because we're using this heuristic of applying selections and projections as low as possible, we're always going to ask, what columns can we throw away? What projections can we do? And what selections can we apply now so that we can start filtering things early? We'll always ask that on the way. And those things will happen on the fly, because after all, throwing away columns from a tuple, you can do it every tuple as it comes by. And throwing away tuples, you can also just examine the tuple and decide whether to throw it away. So selection and projection have no I/O cost. They're done on the fly, and we do them as early as possible. Because of that, we're not even going to draw them in our query plans. Because of course, you apply any selections on S right when you access S. And of course, you throw away any columns of S that you don't need up here. Okay? All right. The other thing that happens with single table queries is, if it's truly a single table query and there's no other joins, then the results would be pipelined into a group by or an aggregate or what have you, potentially. Right? That won't come up in this discussion because we're looking at multi-table queries with joins. But if it were a single table query, we would pipeline things into grouping and aggregation. So let's look at these single relation sub-plans. All right? Well, there's a bunch of cases that may apply for our query. One is that there's an index on a primary key of the table. So maybe we know some schema information that this is a primary key. And that index matches one of the where clauses. All right? One of the outer conjunctions, outer conjuncts of the where clause is a selection on the primary key. If that's true, what's the cost? The cost is you walk down the tree. That height is stored in the catalog, right? Height I. And then you go do one I/O into the heap file if it's alternative 2 or alternative 3 to get the one record that matches on that primary key, right? So the cost of index I on a primary key would be height I plus 1. Second possibility, you may have a clustered index, also called I, all right, that matches one or more of your selection clauses in your where clause. In that case, clustered index, right? So remember the picture with clustered indexes. This is the index. This is the heap file. And if there's a range in the index you're going to search, most of the pointers in that range will be neatly ordered the same way in the heap file, right? Clustered index, so that you'll fetch each one of these blocks of the heap file only once, right? That's the advantage of clustered indexes. So in that case, it's how many pages of the index will we look at? Well, it's the size of the index in total times the reduction factor, approximately. Right? Certainly at the leaf level of this index, we'll look at the reduction factor times the size of the index. Okay? And remember, because the index is very high fan out, almost all of the index is the leaf level. Right? The top levels are very small in a B tree because they're just very wide indexes. So we will, as a coarse approximation, say the number of index pages we touch is just reduction factor times size of the index. And the number of heap file pages we touch is also reduction factor times size of the heap file, because we're going to look at each one of these pages exactly once. So if this is a 30% selectivity, then we'll look at approximately 30% of the index pages, and we'll look at 30% of the heap file pages. And that's what that expression in the second line of costs for clustered indexes says. If it's an unclustered index, of course, we know that it's worse, because what's going to happen here in this 30% is spaghetti nightmare. Right? These tuples are going to go all over the place. Right? And you're going to end up touching 30% or whatever reduction factor of the index, but you're going to end up touching a percentage of the heap file that corresponds to an I/O probably per tuple. Because every one of these pointers you chase is like a random I/O in this file. Okay? And so in that case, it's the number of pages of I plus the number of tuples of R times the reduction factors that match. Okay? And then finally, of course, the sequential scan of just the heap file is just the size of the heap file. So all of these constants are constants that were in the Selinger catalog, right? And these are the formulas to compute the base table costs. If for some reason the query was select distinct and it was really just one table, then the output of this we'd also have to pay for sorting or hashing to remove the duplicates. That's what this detail at the bottom is. But we're going to look at multi-table queries in a second. So for multi-table queries, you wouldn't worry about that. So let's look at a quick example to make sure that we clarify this point. Here's our little query. It's a single table query on Sailor's S where S.rating equals 8. Right? And the only column we're getting out is SID. So as we scan these sailors, the only columns we care about are SID and rating, right? And we're going to apply the rating on the fly. All right? Now, if we have an index on rating, all right, rating is not the primary key of the sailors table. The cardinality of the output, because we decided uniformity assumption, there's 10 distinct ratings. This is equality. So this is 1/10 of the tuples will match this based on this uniformity assumption. So the cardinality is going to be 1/10 times 1 over the number of distinct keys. 1/10, which is 1 over the number of distinct keys, times the number of tuples. There's 40,000 tuples. So we expect to have 4,000 tuples in the output, okay? If it's a clustered index, we should look at 1/10 of the index pages and 1/10 of the heap file pages, right? So it's 1/10 times 50 for the index plus 500 for the heap file. We'll retrieve about 55 pages. That's the cost of that plan using the clustered index. The cost of a plan, if it happens to be an unclustered index, is 1/10 times 50 pages here and 40,000 random IOs down here. 1/10 of that is 4,000 plus 5 is 4,005. Okay? So those are your costs for a clustered index for an unclustered index on rating. If you have an index on SID, well, gosh, you could use it, okay, as your access method for this query. You could. Right? It's a legal access path that will get you all the sailors, but you're going to have to go through that index and look at every single entry in the leaves, right? Because there's no predicate on SID. That's okay. You can do that. You have to retrieve all the tuples and all the pages. If it's a clustered index, the cost is going to be 50 plus 500. If it's an unclustered index, it's going to be look at all of the index, and for each tuple in the table, look at every, do an IO, right? So it's 50 plus 40,000. So this is a crazy plan. It's a terrible plan. But the optimizer will enumerate it because it enumerates stuff, okay? And that's fine. It'll prune it away in a minute because it's going to say it's too expensive.
So does SQL usually do kind of a group by under the covers?
No.
What do you do like for just like kind of underneath group by SID rating, since that's all?
Let me rephrase your question, maybe. What a good query engine might do in this case is to throw away, as it reads things from the disk, any attributes that it doesn't need. So it would project to just SID and rating. But it wouldn't remove duplicates the way a group by would, because it needs to keep the same number of tuples on the way out. So the question was, would SQL do a group by under the covers? The answer is no. Would a query engine throw away some of the columns? That kind of depends, to be honest. I mean, if your table is laid out on disk and you're bringing it by pages into the buffer pool, you'll just be reading the tuples the way they are in the buffer pool. You're never copying them out of the buffer pool. So there's no real notion of throwing away the columns. They're just there on the page as it comes into the buffer pool, and you never copy them again. If you were feeding this into another algorithm, like a join upstream, then you would potentially throw away the columns as you pass the tuples down the pipeline and copy them. Question? Yes?
Going back a bit, you said before that you apply projection differently in
Yeah.
I forgot how many pages do I have actually so
Good question. Okay. To answer these questions properly, I have to back up a little bit, and I'm thinking I will do that in a second. All right, so hold that thought, and we'll come back to it. Yes? Literally, this index is a data structure on disk. It's a file. How many pages are in that file? In the whole thing. Yeah. So if we're looking at an index on SID, look at the query. The query doesn't have a where clause on SID. Okay, so we have to look at all the tuples to check their ratings. And to do that, what you could do is you could walk down the left hand of the index and then walk the leaves of the index in order of SID and access the tuples. If the thing was clustered on SID, that would be pretty similar to just scanning the heap file, right? Because things would be clustered in the same order in the leaves of the index and in the heap file. But you still pay the cost of doing this and walking across the leaves, all right? Which is stupid. I mean, to be very clear, if you were thinking about the problem as a person, you would just jump to a file scan instead of doing that. The point is that here we're going to be a little brute force. We're going to enumerate a bunch of plans, and then we're going to only pick the cheapest one. And that's just part of searching the space in an exhaustive way. Okay? So the last thing you could do here, which is another option, is you don't use an index, you do a file scan, and the cost is 500. So an optimizer, if you don't do any kind of rule-based pruning, if you just enumerate all possible plans based on all possible data structures that you have stored on disk, you could look at any index that's on any attribute mentioned in the query. You could look at the heap file scan if there's a heap file. You get their costs, and you pick the cheapest. Okay? And in this case, pretty obviously, the cheapest would be to use the rating clustered index if it existed. If it wasn't clustered, though, the best thing to do would be the file scan. And the file scan is always going to be better than an index on some attribute that's not in the where clause, actually. So that was probably something we should have had a rule in the optimizer to prune out. That's OK. This sort of got us thinking. So sometimes in the optimizer, you can add some things that will prune things out because they could never win. But you can always have the optimizer enumerate them and throw them out as you go. Throw out the more expensive things as you go. OK, so this is a little brute forcey. So I want to back out now. We're going to take a pause unless there's any more questions on single table cost estimation and enumeration. This is kind of almost the same thing we've always done. This is just cost estimation. We're looking at all the plans, and we're looking at their costs. All right? We haven't done anything interesting algorithmically. That happens in the inductive step when we look at multi-table queries. But let me take a pause because I was getting two questions that were very related about projection on the fly and what does that really mean. All right? So let's be careful and think about how we described how tuples get into query plans in the first place in a traditional relational database. Tuples live on the disk in pages, right? And when I draw a picture like this one, and I say we're going to scan this heap file, what do I really mean? What I mean is we're going to look at a sequence of pages on the disk, and we're going to request the buffer pool load them. We're going to say, hey, buffer pool, here's page number 1 of that file. Here's page number 2 of that file, right, et cetera. I'll say, hey, buffer pool, I want to see page number 1 of that file. If it's not in the buffer pool, it will evict something, and then bring page 1 in here somewhere, right? And then there's an algorithm over here like selection. Or really, it's just file scan. And the file scan query processing algorithm is going to go through every tuple on this page and decide whether to pass it along to the output. Okay? It's actually not going to copy these tuples. It's going to look at them in memory in the buffer pool. Okay? So these are tuples remain in the buffer pool. Projection actually doesn't do anything here. We don't really project anything. We just, until we form an output tuple, we don't project anything. When we form an output tuple, that is to say we're going to pass this maybe to a client library that's going to send it off to a client on the internet if it's a single table query, okay? So there's a connected client like pSQL that you guys type, right? pSQL connects to the Postgres server through, say, TCP/IP. There's various ways it could connect. That's one. All right. When this thing is actually generating an output tuple that's going to be sent over the wire to the client, then it will copy it out of the buffer pool, project out any columns it didn't need, okay, and send just, in this case, the SID. But it applied the selection on rating just by looking at the tuple in the buffer pool. It said this tuple here, is the rating equal to 8? No. Let's move on. This tuple here is the rating greater than or equal to 8. There's no projection involved with that selection, okay? That said, suppose that the next step of the plan isn't output to the screen, but it's, say, a join. So we've got a file scan, passing things into a join. And maybe the join is, again, on SID equals SID. So this is a file scan of Sailor. And this is a file scan of Reserve. And this is a nested loops join. Do we need to copy the Sailor tuples out of the buffer pool into heap memory somewhere in order to execute this join? Actually, no, we don't. We can continue to pass a pointer to a tuple here. So this join algorithm actually doesn't get a tuple as its input. It gets a pointer to a place in the buffer pool that holds that tuple as an input. Right? And we never copy that tuple at all. It stays in the buffer pool, and just a handle to it's passed here. And all of this looping that happens in this nested loops join never copies any tuples at all. Which is good, because copies actually are really expensive. They blow the caches in your processor and all that stuff. So generally speaking, when possible, we'll leave things in the buffer pool, which means there's no projection that's really happened. All right? However, if this thing is a hash join, well, you know how hash join works, right? We're going to take the tuple out of the buffer pool. We're going to copy it into a hash table. And then we want to apply a projection before we put it in the hash table. All right? So anytime you're going to copy something out of the buffer pool into the heap memory of a query processor, that's the point where you want to do a projection. Make sense? So in memory, while you're looking at queries, when we talk about tuples, some tuples are by reference, and we leave them in the buffer pool. But sometimes when necessary, tuples get copied by value and stuck into data structures. All right? And you can be careful about that. Sometimes you want to leave the data structures pointing back to the buffer pool, and sometimes you don't. Remember that if we copy a tuple out of here, if we take a tuple out of here, we put it in the hash table of our join, and we do it by reference, that would mean we would have to keep this page pinned in the buffer pool. That's not cool. You're not allowed to pin things in the buffer pool for very long. Okay, so while something's by reference in a query, it has to be on a pinned page. That's okay for the outer of for the inner of a nested loops join. It may not be okay for the outer of a nested loops join, depending on how you implement things. So another reason you copy stuff, I'll slow down. Another reason you may copy something out of the buffer pool is so you can unpin the page in the buffer pool. Okay, and that'll put less pressure on your replacement policy. Right? So if something's by reference in the buffer pool in a live query, that buffer pool page has to be pinned. Does that make sense? Okay. So that's projection only matters when you copy things, because then the result of the copy is smaller, which is good. It takes up less memory. All right. And we'll do this case by case. We'll probably not talk about this again in this class, but in future you should be thinking about this. And of course, when we think about our data structures in our joins, we do care that you apply projections, and you will be potentially asked about that on exams. Okay? All right. The question that you asked was, is it ever a bad idea to do projection early? Does it ever cost to do projection early? And I guess what I'd say is, if by projection you mean copy it out of the buffer pool in order to achieve the effect of projection, yeah, you don't always want to do that, because sometimes there's no reason to copy it. Does that make sense? Oh, that was your question. Does that make sense? Yeah, good, cool. Other than that, I mean, if you're going to do a copy anyway, you might as well have the output of that copy be as small as possible. I've never heard of an expensive projection otherwise. All right, so that was some pretty low-level details. By the way, and I think I never mentioned this, we wrote a really exhaustive paper called Architecture of a Database System. If you really care about this stuff, we wrote about really under the covers how is this stuff implemented that's not in your textbook. So I wrote this with Mike Stonebreaker, who is my master's advisor, who was the Ingress and Postgres inventor, and a guy named James Hamilton, who worked on IBM DB2, Microsoft SQL Server, Microsoft NTFS, and now is like lord of all operations at Amazon. Really like well-versed guy in the industry. And we talk about exactly what goes on under the covers, including things like, okay, where's the tuple in memory really? We have this conversation in that paper. So if you're really curious and you don't remember today's lecture, you want to know more, Google for that thing. It's very detailed, more detailed than most of you care about. With that, I'm going to pop the stack and go back to query optimization. We good? Okay. Where were we? Let's resituate ourselves. Plan space, cost estimation. No, we were in the search strategy. We were learning system R. We had finished dealing with single table queries or single tables within a multi-table query. And now we're on to the induction step. Okay? The second line here. For a multiple relation plan, how do we do induction on single relation subplans? And this is how it's going to go. All right? This is where the dynamic programming comes in. We're only going to look at left deep trees. You know that. All right? Because they pipeline nicely. So none of those. And as we said at the beginning of lecture, left deep plans differ in the order of the relations, ABCD versus BACD versus ACBD, et cetera. They differ in the access method for each relation. So is it a heap file scan, or is it one of the B trees, et cetera? And they differ in the join method. All right? That's the only things you can do with a picture of a left deep tree. You can move the relations around, and you can change the annotations of what's the access method of the leaves, what's the join algorithms of the joins. That's it. Okay? All right, so we're going to enumerate this in n passes. Pass 1 is going to do what we just described. We're going to find the best one relation plan for each of the base relations. So we'll find the best way to access A, the best way to access B, the best way to access C, and D. And we'll do them independently. In pass I, inductively, we will have found the best way to produce plans of size I-1 tables. And in pass I, what we're going to do is find plans that are of I tables. And we'll find the best one of those. So what's the best way to join a result of an I-1 relation plan, which will be the outer of our join? So think about an I-1 tall tree here. Maybe I-1 is 2. A join B join C. And then we're going to ask, how do we join that to D? How do we join it to E? How do we join BDE to C, et cetera? So we'll find all these three-way plans and add one to make them four-way plans. I'll go through this in detail now. For each subset of these relations, after we look at all the I-way plans, we're going to keep the cheapest I-way plan for each subset of relations. Right? For each subset of 4 relations, let's say, A, B, C, D, A, B, C, E, B, C, D, E, et cetera, we'll keep the best plan for each one of those subsets, the one that's cheapest. We will also keep something called the cheapest plan for each interesting order of the tuples. And I'll show you what that means in a sec. So we're actually, as we go, we're pruning, but we're keeping the cheapest plan and the cheapest plan for each interesting order. So the pruning is not down to just one thing. The pruning is down to a few things at each step of this recursion. We're going to have a dynamic programming table. It's going to look kind of like this. These are the attributes of our dynamic programming table relationally. Okay, so if you can think of this dynamic programming table as a table, this is what it has. It has the subset of tables in the from clause is one of the attributes. So for tables R, S, we're going to have the best plan for no interesting order, so just the best plan overall. So the interesting order columns in the first row is none. And the best plan for that is, let's say, a hash join of R and S. So we looked at all the possible ways to join these things. We estimated their costs. And we said, by golly, the best, cheapest plan for joining R and S is hash join. And its cost was 1,000. All right? So that's the best plan. That's the winner for that pair. But in addition, we'll keep for that pair the best plan for the interesting order R.A, S.B. Suppose you wanted the output of this join ordered R.A, S.B. Why would you want it that way? I'll talk about that in a minute. But suppose you cared about it being ordered. In that case, the best plan was a sort merge join, which cost 1,500. Okay? We're going to keep that too. Now, you might ask, what is an interesting order and what makes it interesting and why would I want it? An intermediate result has a, quote, interesting order if it is sorted by any of the order by attributes in the query. Suppose the query said at the top, order by r.a, comma s.b. Well, rather than using the first plan and sorting, it would be cheaper to use the second plan, okay? So if there's an order by clause in the query, as you go, you should keep track of things that will give you that ordered output. Otherwise, later on, you're going to have to pay for the cost of sorting. All right? But the same applies to group by. If there's a group by later on r.a, comma s.b, we could save ourselves the trouble of grouping later on if it happens that our plan from below just produces things in the right order. All right? And then the final thing that might be interesting later on is maybe you can order this by some attributes that we still need to join on. Like maybe this is going to be joined with t, and t joins on r.a. Okay? Well, then having this sorted means maybe we can do a really cheap sort merge join with t. All right? So it's an interesting order to see that it's ordered by r.a s.b because it could be used in a join with t on r.a. So things are interesting if there's still work to be done later in the query that's either order by, group by, or join on that attribute. Okay, so those are our interesting orders. And with that, here's how we yeah, here's how we put things together. Yes. So first of all, the first bullet on here, this is kind of the recursion rule. It says if you have a plan in one of these tables of I minus 1 tuple, of I minus 1 tables. So these plans have 2 tables in them, R and S. Okay? So each one of these is a plan for a 2-table join. Suppose we're now building 3-table join plans out of the 2-table join. All right? When do you join a 2-table plan with a 3-table plan? So in particular, let's take an example. Suppose our query is on R, S, T, and U, 4 tables. And we had those R and S joins. So we had the best way of joining R and S. All right? Actually, we had 2 ways of joining R and S. One was best, and one was interesting ordered best. Okay? Let's encapsulate that. Somehow we're going to join up R and S. And now we want to join in something else to make a 3-way plan. Okay? Should we join it with T? Should we join it with U? All right, well, we will find the best way to join it with T. We should do it if there's a join condition in the query between them. If it says where something equals T dot something, and the something here is R or S. Okay? If there's a join predicate between this subplan and T, then we can put a proper join in here and join T onto this. And we'll look at all possible ways of joining the best thing here with T. Note, by the way, that the join cost formula here only cares about this number of tuples flowing along this edge. It does not care what plan is down here. That's why the dynamic programming works. We can optimize the subplan, and making the best decision about the next level up, we don't care what the result was here. We just want it to be good. Right? So we're doing this bottom up, and we're getting optimal little subplans and putting them together into bigger optimal plans. OK, so given that, we will join T in if there's a join predicate on this subtree and T. And if we do that, then we can sort of tick this join predicate off. We're done with it. All right? So we're going to be pulling things out of the where clause. We already took out of the where clause all the RS things. Right? But it's possible that we get to the point where we have R and we're trying to join in T, and there's nothing left in the where clause that hasn't been joined up. So let me give you an example of that. It's a bad example, but it's a legal example. Maybe it's not bad. Select star from R, comma S, comma T, comma U, where R dot A equals S dot B, semicolon. OK? So yes, we want to join up R and S because they have a join predicate between them. When it's time to look at T and U, there's nothing left in the where clause to work with here, right? We're all done. We're forced now to do Cartesian products because the query asked for them. Right? The query says, I want you to cross product with T and U. And so at that point, we will consider tacking T on and putting a cross product. But if there's anything else we could have done, we wouldn't tack that cross product on. So for example, if we had this and R dot C equals U dot A, We would not even consider putting T here with the cross product. We would look only at joining with U because there's still that U predicate to be joined up, right? This thing, R.C equals U.A. So the rule in the system R algorithm is you keep building up these optimal subplans and then joining them with joins, not cross products, but joins with other tables to make one bigger plans until you run out of joins. And then you start doing cross products at the top. Right, so essentially what we're doing is avoiding or postponing the Cartesian products till the tops of the plans. Okay? And that's all there is to this algorithm. And we're going to enumerate, remember, for RS, all the ways to join it with U, all the join algorithms, all the access methods. Then we're going to find the cheapest of these and call it RSU and be done. And we'll find the cheapest for each interesting order, if there were any, and save those two. And everything else gets thrown away, and we recurse. All right? If there's a query, if your query has order by or group by or aggregation, that all happens at the very end. So at the end, what we've got is we've got tables that have, query plans that have all the tables in them. All the joins have been done. And all that's left to do is group by, order by, and aggregation, et cetera. At the tops of these plans, if there's no interesting orders and you want to do group by, you'll stick a hash or a sort and do your group by. But you'll also consider, if there is an interesting order, using that interesting order for the group by. And then you'll compare the cost of the best plan with the group by operator on it and the interesting ordered plan with the free group by operator on top of it. And whichever of those is cheaper, you'll use. Make sense? So the aggregation and the group by happens at the end, and that's the point where you prune out any remaining interesting orders and you choose the truly optimal plan for the whole query. Okay. Now, even though we're pruning as we go, because each subplan, plans of size 2, plans of size 3, we're pruning as we go to only the best plans and the best interesting orders, this is still exponential. Okay, and it should be obvious why. Even though there's many ways to join R and S, at the end of the day, we're going to enumerate all strings of RSTU and permutations of them. We'll do RSTU, RTUS, STUR, et cetera. It's just that we won't keep all the possible plans for all of those orders. All right, but there's factorial many orders. We know that, right? So that's exponential right there. All right, so it is exponential. Do recall in practice that the costing is IOs and CPUs. We've been sort of eliding the CPUs. But that's pretty much the whole thing. So let's look at an example to clarify this. All right, here's our example. We've got sailors, reserves, and boats. It's a three-way join. We've got join predicates between sailors and reserves, between reserves and boats. Boat color equals red, group by SID. So on the first pass, we're going to get the best plans for accessing sailor, the best plan for accessing reserve, and the best plan for accessing boat. All right, and what are our options? For sailors and reserves, here's our data structures. We have hash indexes in this example because the book does, and don't worry about hash and how they work. They're just like B trees, all right? Except they're hashy. So we have sailors and reserves. For those, we could do a file scan, or look at the indexes. We could use that reserves.bid clustered index because it might be an interesting order for a subsequent join, right? And we could use the B plus tree on sailors.sid because it could be an interesting order for a subsequent join. Or we could use the B plus tree on color for boats because it is in the where clause. Right, so those are all the access methods that are relevant to this plan. And let's look at all their costs. And then for each relation, we'll save the cheapest plan and the cheapest interestingly ordered plan. And maybe we get a table that kind of looks like this after that. Sailors, reserves, and boats. The first two have file scans that have no interesting order. The third one, the winning plan, is to use the B tree on color. It's because you're doing basically lookup by color in this B tree. It's clustered, it's cheap. And you prune away this file scan on boats by cost. All right, and then for interesting orders, we keep reserves on BID and sailors on SID. So we've got one plan for the optimal access and then some interesting order plans. That's the end of pass 1. In pass 2 now, what we're going to do is we're going to put together those one-table plans into all two-table plans. So here's a list of a whole bunch of two-table plans we could build. All right, file scan of reserves joined with boats. We'll have to do all the join algorithms for that. File scan of reserves joined with sailors. Reserves B tree with boats, right, et cetera, et cetera, et cetera. We'll look at all these combinations and all the join algorithms on top of them. And then for each one of those pairs, reserves, boats, sailors, reserves, boats, sailors, We'll keep the cheapest plan for each pair, and we'll keep the cheapest interestingly ordered plan. And now the interesting orders don't care about the joins we've already done. They only care about the joins that remain to be done, and the, whatever it was, group by or order by clause. I can't remember what we had. We had a group by clause, so SID is interesting order. All right? And maybe we get a table that has some of these things in it, and it goes on from here. This is not the full table. But now we've got two-way plans in it, like boats, comma, reserves has an interesting ordered plan where you do a sort merge join on the B tree on boats.color, which is, and the file scan of reserves. The result of that is ordered by b.bid. It's also ordered by r.bid. Okay, so it's got two interesting orders that are independent of each other. We keep it around because those BIDs could be used, particularly the r.bid could be used with a subsequent join with s, right? Okay, etc. And past 3 and beyond, you take the two table plans, all of which we've now enumerated, and you stick on the thing they're missing. Whichever of the three relations that two table plan is missing, that's the thing you join on. Okay, so take something like we have boats B tree on color. Yeah, so we take the two table plan that was B plus tree on boats joined with reserves, and then we add to it sailors with the B tree SID using sort merge join. So that would be a thing we would add on in this step. And then we would consider the cost of all of those three-way plans. Because this is a three-table query, then we're done, right? So here's our query. Once we get the best three-way plan, sailors, reserves, and boats, the only question is the interesting order on SID for the group by. Is there something that already has an interesting order, or do we have to pay for the group by with a hash, okay? And that's the last question. If there's something with an interesting order on SID, group by is free. But if it's much more expensive than, if it's much cheaper to get it without an interesting order, maybe it's cheaper to just take the cheaper plan and sort. And so we'll just check that out, decide whichever one's cheaper, and that'll be our final plan. All right. So we worked through an example. This is the dynamic programming algorithm. It goes in rounds by numbers of tables, and then we put these things together. It's pretty much keeping the cheapest thing every time with this detail of interesting orders. Any questions? It's a lot. It's a pretty simple algorithm, really. But it helps to work through some examples and to draw the trees for the examples as you go. So I encourage you to do that. OK. With that, we've covered all three of the pillars or parts of Query Optimizer. That's the search strategy. Cost estimation is what it is. It was used to prune during the search strategy. The plan space defined how we built up these trees, right? Left deep trees that we built piece by piece. That's everything. All right. So what we're going to do is sort of set aside query optimization for a second. Imagine you have a query optimizer, and it does all this, and it works great. We left sort of something out, which is who decided what indexes there were? Right? During this optimizer thing, we said, well, maybe there's an index like this, or maybe there's an index like that. Who decides what indexes there are? Traditionally, the answer is the database administrator decides what indexes there are. And there's good reason for that. It's going to cost you a lot in disk space to build an index. They're often as big as the tables that they index. Not always, but a large fraction of the tables they index. And every time you do an update to that table, you have to update the index. So they slow down your updates. So choosing indexes, you really need to understand the workload and need to understand what's important in that workload. Like maybe update queries are really important, and these kinds of queries with lots of joins are not so important. So you optimize for the updates. You don't build any indexes. But that's usually a human design decision. It's not usually left to a machine. So traditionally, this was all designed by people, by database administrators. And so there's this task, which if you remember, and you probably don't, but when we talked about database design, way near the bottom of the list of things, there's like requirements analysis and conceptual design and schema refinement. Way down at the bottom was physical database design. It's time to talk about that. Now you know the optimizer looks like. Now you want to think about, OK, what indexes should I build? So the query optimizer will do what it does with indexes and clustering and all that. But the DBA is expected to decide what indexes to build, which ones are clustered, et cetera. And as you can imagine, having been through this, a good DBA needs to have a sense of what the optimizer is going to do. If you're going to add an index, what queries are going to go faster and how much faster? Well, that depends a lot on what the optimizer's plan space is and what plans it's going to pick, right? If you know something about query optimization and you see that there's a plan that always is picking the sort merge join and it's really expensive, you might look at that and go, I see why the optimizer is doing that. I think if I added an index here, it would choose a index nested loops join, then it would go really quick. Right? But you sort of need to get your head at least the cost estimation problem. You need to understand why plans are cheap or expensive. And maybe you also want to know what plan the optimizer might choose, which is the other two legs of the stool, in order to choose good indexes. So a good DBA has a good understanding of all this stuff. So one key decision a database administrator might make is what indexes to build. Which tables should have indexes? What fields should be in the search key? Do you have one index with, say, lots of columns in the search key? Or do you have many indexes, one in each column? And should these indexes be clustered or not? So we're going to go through that questioning process now for the last 10 minutes of class. It's intimately tied with the optimizer, right? It's the things that give the optimizer a bigger plan space for physical plan selection. Adding an index adds possible access methods, which combinatorially increases the number of join plans we could look at. Okay. So here's a greedy approach to choosing what indexes to add to your database, if you're a database administrator. Think about your queries that you get, generally speaking. You can be sloppy about this. Be like, there's the queries that update the grades. There's the queries that produce the grade reports. There's the queries where the students can log in and check their own grades. Like, which ones of these is the most important? Right, so you rank order the kinds of queries you get, and you consider them in turn. So the most important queries, let's say, are, I don't know, entering grades, because that happens a lot, because we change our minds about your grades all the time. We don't do that, but probably a bad example. Not a high update rate application, but that's okay. Imagine a scenario like shopping, all right? So the transactions table at a website that does shopping, we add things to it all the time. So those have to go really fast. You always want people to be able to check out fast, because that's when they spend their money. Don't want to get in the way. All right, so that's the most important thing first. What would be the best plan for that transaction based on what we have today? Could you do better if you added another index? Could you make that top most important query faster by adding another index? If so, go for it. And then iterate. So that's kind of the greedy approach. And you do this till you kind of run out of budget. What's budget? Could be disk space. Or it could be the cost of doing updates, right? Like, I can have like 3 indexes on this thing before updates get too slow. What 3 indexes should I have? Okay? So you have to consider the impact on updates. Indexes make queries go faster and updates slower, and they require disk space. So that's kind of your budget in this greedy algorithm. You keep doing it till you run out of space, or your updates are going to get too slow. All right. Now, what index should you build, though? Well, here's the things you have to think about. The attributes mentioned in the where clause, those are the indexes that you care about. Any other indexes are kind of a waste of time, all right? Unless they provide sort orders for sort merge join. Scanning an index will give you things in order, right? That might be interesting to you, all right? But attributes mentioned in a where clause are definitely candidates. Remember, this is really important, and it's a super easy thing to ask on a test. So test question alert. If I give you a query and the where clause is a range predicate, right, this may actually have been on the midterm for all I can remember. I can't remember now. If the query has a range predicate, like rating greater than 5, remember that a clustered index will help, right? Because you're going to scan across many tuples will match that in the index, and you'll follow a pointer from each one of those matching tuples. And if it's clustered, that'll be few IOs in the heap file. And if it's unclustered, it'll be an IO per tuple, right? So if you have range queries, clustering will help. If you have equality queries, rating equals 5, does clustering help? How many people think clustering only helps for range queries? It does not help for equality queries. How many people think clustering helps for equality queries also? All right. For those of you who raised your hand, why would that be true? Right, right. So this was a bit of a giveaway, right? Obviously, there's more than one sailor with rating equals 5. When you get bottom of the index and you're looking at all the 5s, if it's unclustered, you'll do random IOs for all of those 5s, right? Each 5 is a different random IO. Now, if it's a key column, like SID equals 5, There's only going to be one thing that you chase, and so clustering won't help. So equality on key columns is the case where clustering doesn't matter, okay? And so an unclustered index is fine. Remember, you only get to sort the heap file one way, so you can only kind of cluster on sort of one index. So it's kind of a big decision. Exact match conditions do require clustering is the answer to this thing, if they're not on key columns. All right. Obviously, you'd like to get more bang for your buck, so the utility of an index is the number or the importance of the queries, the many queries that it may help with. All right, but choose your clustering wisely. So here's an example. We got a join on dno of emp and dept, and we've got a selection on the department name, which is toy. So you could build an index on dname to support the toy selection. And if you do that, you know what? The result's going to be pretty small because there's only one department called toy. Dname is probably a key. All right, which means that the join of emp and dept is going to be super cheap. You're joining emp with one tuple, right? So that you don't need an index on dno once you've got an index on dname for this query. Because you made the thing so small that you wouldn't use the index for the join. You'd just use the index for the and dname equals toy. So that's interesting. If you built an index instead on dno, all right, then you could, for each employee, you could look up the department tuple. So that's another way to do it. Probably not as good, let's say. But maybe that index on dno would be useful elsewhere in some other query. Oh, actually, I did this backwards. What it says here, forgive me, is not an index on d.dno, but e.dno on the emp table. Okay? So an index on e.dno would allow us to do a query plan that scans dept and looks up tuples in emp, right? Now, we could have both of these indexes. You could look up the one toy department tuple, and then you could use a B-tree index on e.dno to look up the one, or to look up the employees that work in that one department. So that one could help too. They could both help, okay? Now, if the where clause also included and e.age equals 25, think about this one now. You could retrieve the emp tuples using that index, and then you could choose a join with the toy department dept tuples, and there's going to be very few emps and very few depts. And so any join will do, and you don't really need an index for the join at all. Okay? So in that case, that might be just as good as building the e.dno index, would be to just index on age if there was this age predicate. So if we already had an age index, there'd be no reason to build the e.dno index. And you got to kind of think all this stuff through. And the only way you can think it through is if you understand query plans and query optimizers, right? If you start running around willy-nilly creating indexes, you're going to do a lousy job. So that's one example. Here's a second example. Emp and dept again. Salary is now a range predicate on emp, but we've got an equality predicate on hobby, right, and the join predicate again. All the selections are on emp. So all those where clauses that are on a single table are on emp. So probably whatever plan we do is going to filter emp down using some indexes if we can. That's going to lead to a really small emp. Dept is probably not that big anyway because it's just departments. And so any indexes we build should probably be on emp, right? Let me say that the other way around. Emp is really small. Sorry. After all those selections, emp is really small. So if we're going to do a lookup, the lookup should be into dept on an index nested loops join. Let me draw that picture. I was making a different point out loud than the slide was making. And I think we'll close with this point. The first bullet of the slide, to clarify so I don't confuse you with what I said. Look, emp is going to be well selected upon. And even if we scan it, we can filter it on hobby. And we can filter it on the other thing, which was salary, before we do any join. And so if we're going to do an index nested loops join, probably best to have this be the outer table and do index probes on dept, rather than the other way around, because there's probably more departments in total than there are employees who are stamp collectors with that salary range. All right, so in terms of what indexes would help with joins, probably better to build an index on dept than on emp, because emp is already going to be relatively few tuples. Make sense? That's what that first bullet is saying. Okay. What index should we build on emp? Well, look, we could build an index on salary also. So this thing down here could be an index on salary. And it would be a range index, right? It better be clustered if you do that. Or we could build an index instead on emp.hobby, which would be a single value. Now, many people may be stamp collectors, mind you. It's a pretty popular hobby. All right? And then we would select on salary. So you have to decide what's the selectivity of hobbies being stamp versus the selectivity of salaries being in the range of 10,000 to 20,000, right? And if you don't know anything about the distribution, the uniformity assumption would say that equality selections are probably better than range selections. So maybe you'd build it on hobbies. Bottom line, a bunch of eyeballing and heuristic thinking will help. If you understand how the optimizer works, you can do that heuristic thinking in a sensible way. And where we're going to go next time for about a slide or two is to say, I will give some examples of this. There are systems, the end of this, where was it? Here. Modern systems will do some of this for you. So there's tuning wizards in like IBM's product and Microsoft's product that will go through this thought process kind of for you based on a log of queries they've seen in the past. So these systems will log every query they ever see, and then they'll, if you want, analyze that log to try to do this thought process for you. What's the most important query? It's the one that gets asked the most often, et cetera. How much better would this query be if we added another index? And they'll go through that process for you and make suggestions, and you can choose the suggestions or not. We'll talk about this again when we get back next time. We'll finish with index tuning, and then we will be done with the single user relational database stack and talk about text search instead. So that's going to happen next time. Good luck. Homework is due 2 weeks from today.